There is a particle 3,477 times heavier than the electron. It lives for less than a trillionth of a second, then disappears. Every atom, every molecule, every living thing was built from something else entirely. And physics cannot explain why it exists. This is the Tau. It sits inside the most successful scientific theory ever built, a theory accurate to 12 decimal places, and it remains a mystery that theory simply refuses to solve. We will trace its unlikely discovery, follow the growing cracks it may be opening in physics right now, and arrive at a question that has stood unanswered for 50 years. If you enjoy this journey, like and subscribe. We begin. There is a particle hidden inside the laws of physics that weighs more than a proton, vanishes in less than a trillionth of a second, and plays no known role in anything you have ever touched. Every atom in your body is assembled from electrons and the quarks locked inside protons and neutrons. Stars burn for billions of years through nuclear reactions that never call on this particle. Galaxies spin and collide across distances so vast that light takes billions of years to cross them, and still this particle is not involved. The entire visible architecture of the universe, from the smallest living cell to the largest structure astronomers have ever mapped, runs perfectly well without it. And yet it is there, woven into the bedrock of nature, measured to extraordinary precision and completely unexplained. It is called the Tau. And in half a century of trying, physics has never answered the simplest question you could ask about it. Why does it exist? To understand why that question is so unsettling, you need to know one thing about the universe's architecture. The matter that builds everything you have ever seen or touched comes from exactly 3 types of particles. One kind of quark, combined in pairs and triplets to form the proton and the neutron. The electron, and the electron neutrino, a ghostly particle that passes through solid rock as easily as light passes through glass. That is all the universe needs. 3 particles arranged in countless ways, and you get atoms, molecules, chemistry, biology, galaxies, and everything else. Nature made a second set of 3 anyway, heavier versions of the same particles, all of them unstable, none of them present in ordinary matter. Strange, perhaps, but possibly forgivable. Then nature made a third set. The Tau is that 3rd generation's version of the electron. It carries the same electric charge. It feels the same forces. It is, in every measurable way of behaving, identical to the electron. The difference is mass. The Tau weighs 3,477 times more than the electron, more than a proton, more than a neutron. It is the heaviest charged lepton in the known universe, and it disappears in less time than it takes light to travel across the width of a human hair. Physics has a framework called the Standard Model that describes every known fundamental particle and how they interact. It is the most precisely tested theory in the history of science. Some of its predictions have been confirmed to more decimal places than almost any other measurement humans have ever attempted. The Standard Model can describe the Tau with beautiful accuracy, its mass, its lifetime, its decay products, the precise fraction of time it spends decaying in each possible way. And the Standard Model cannot tell you why it is there. That gap between extraordinary precision and total ignorance of the underlying reason is what makes the Tau one of the most genuinely troubling objects in physics. The theory measures the Tau perfectly. It cannot explain the Tau at all. Over the next hour, you will see how the Tau was discovered by one man who refused to accept that 2 copies of the electron were enough. You will see what the Tau does, what it tells us about the forces that hold matter together, and where it might be quietly cracking the very laws we thought were absolute. But the deepest part of the journey is the question waiting at both ends. If the universe functions perfectly without the Tau, why is it there at all? To see why the Tau is such a puzzle, You need to see where it lives. Physics has an inventory of every fundamental particle ever discovered, a framework called the Standard Model, which is best understood as a periodic table for the universe itself, going one level deeper than atoms. The list organizes into 3 categories. First, 6 particles called quarks, which combine to form protons, neutrons, and a whole family of short-lived relatives. Second, 6 particles called leptons, which include the electron and everything in its family tree. Third, the force carriers, particles that transmit the fundamental forces between everything else. The photon carries electromagnetism. The gluon carries the strong nuclear force. The W and Z bosons carry the weak nuclear force. And then there is the Higgs boson, the particle responsible for giving mass to all the others. 17 types of fundamental particle. And everything that has ever existed is made from combinations of them. What makes the Standard Model staggering is its accuracy. The theory predicted the Higgs boson nearly 50 years before any machine on Earth was powerful enough to produce one. It predicted the W and Z bosons before they were found. When physicists measure the strength of the electromagnetic force, the theory's prediction matches the measured number to 1 part in 1 billion. No other theory in the history of science has been tested this rigorously and agreed with experiments so consistently. It is, by any fair measure, one of the greatest intellectual achievements in human history. And yet, physicists describe it with an unease that does not go away. The Standard Model works, but it works the way a recipe book works. It tells you precisely how to combine the ingredients and what you will get, without ever telling you where the ingredients came from or who decided which ones belong on the shelf. It contains 17 types of particles because experiments found 17 types. If tomorrow someone discovered an 18th, the ingredients are described, not derived. That is where the Tau's generation enters the picture. Among the 6 leptons inside the Standard Model, there is a structure that the theory measures perfectly and cannot explain at all. The 6 leptons do not form a random collection. They arrange into 3 pairs, each pair nearly identical to the one before it, each one heavier and shorter lived. 3 generations of matter, stacked inside the theory like 3 nearly identical shelves in the same cabinet, with no explanation of why the cabinet has 3 shelves rather than 1 or 7. When physicists look at this structure, 2 reactions tend to appear at once. The first is admiration, because the pattern is precise and strangely beautiful. The second is unease, because something that precise, with no known origin, is usually a sign that something deeper is waiting to be found. The Tau lives at the sharpest corner of that unease. It is the heaviest of the charged leptons, the most extreme member of the most unexplained pattern in the most successful theory ever built. And what comes into focus when you look at each generation in turn is the beginning of understanding how that strangeness grew. Strip away everything complicated, and the generation structure of matter comes down to 1. Observation that should feel stranger the more you think about it. Nature appears to have copied its ingredients. Start with the electron. It carries a specific electric charge, negative, equal in magnitude to the charge of a proton. It has a spin value of 1/2, which places it in the category of particle called a fermion. It interacts through electromagnetism and through the weak nuclear force, and it ignores the strong nuclear force entirely. Those properties are what define a charged lepton, and together they tell you how the particle will behave in any experimental situation you can design. Now take the muon, negative electric charge. Spin 1/2. Electromagnetism and the weak force. Strong force ignored. Identical behavior in every fundamental interaction. Its mass is about 207 times larger than the electrons, but everything about what it does and how it does it is the same. 2 particles, 1 identity, different masses. Now take the tau, negative charge. Spin 1/2. Electromagnetism and the weak force. Strong force ignored. 3,477 times the mass of the electron. An exact copy of the same identity, now so heavy it crosses into territory usually occupied by nuclear particles. This is the generation structure laid bare. 3 charged leptons with identical charges, identical spins, identical force responses, and masses that jump by enormous factors between each step. The same pattern appears in the quarks. The up quark has a partner called the charm quark, a heavier copy, and beyond that, the top quark, so massive that a collection of top quarks would weigh as much as an atom of gold. The down quark has the strange quark, then the bottom quark, each heavier than the last. 3 pairs of quarks, mirroring the 3 pairs of leptons, following the same unexplained pattern across the entire structure of matter. The mass gaps between generations are vast. Going from the electron to the muon is a jump of 207. Going from the muon to the tau is another jump of roughly 17. These are differences of orders of magnitude, deep enough to demand a fundamental explanation, and the standard model simply accepts them as measured facts, the way a table of contents accepts entries without explaining why the book was written. Physicists call this the flavor puzzle, or the generation puzzle, and it has been sitting at the center of particle physics for 50 years without resolution. Why 3 generations? Why these masses? Why does the pattern repeat at all? And why does each repetition arrive so much heavier than the last? The theory has measurements, encoded beautifully into equations, and those equations produce experimental predictions with stunning accuracy. But the reason the ingredients are arranged this way, the reason there are 3 charged leptons and not 1 or 4, is not contained in any equation physicists have written. Every generation of physics students learns this structure in their first courses, and every one of them asks the same question. The answer has been the same for 50 years, and the deeper you look at any one member of this pattern, the sharper that answer becomes. Every copy requires an original. Before the mystery of the tau can land with its full weight, you need to understand what it is copying, because what it is copying is the particle that holds everything together. The electron is, in a very practical sense, the reason matter exists the way it does. Every atom is built on a simple architecture, a dense nucleus carrying positive charge at the center, surrounded by electrons carrying negative charge. The electromagnetic attraction between opposite charges is what keeps electrons bound to their nuclei. That bond is the root of everything. It is why atoms can link into molecules, why molecules can fold into proteins, why proteins can build cells, why cells can build organisms. The electron is the glue between atoms. And without it, the universe contains no stable chemistry, no biology, and nothing you would recognize as matter. The electron is extraordinarily light. Its mass is roughly 500,000 electron volts, a unit physicists use for particle masses at the quantum scale, so small that 2 billion electrons would barely outweigh a single grain of sand. And as far as any experiment in the history of physics has been able to determine, the electron is permanent. It does not decay. There is nothing lighter for it to turn into while preserving its quantum properties. So it persists, indefinitely, doing its work. That permanence follows directly from the physics. The electron is the lightest particle in its class, and decay requires a lighter final state. For the electron, no lighter final state with matching quantum properties exists. Every possible exit is closed by the laws of conservation, and so the electron stays. It holds atoms together. It carries electricity through wires. It fires the signals that constitute thought. It is so fundamental to the structure of matter that removing it from the equations produces a universe with no chemistry at all. The electron couples to the Higgs field, the field responsible for giving mass to fundamental particles, with an extraordinarily small coupling. Physicists call this the Yukawa coupling, after the Japanese physicist who described the mechanism. The electron's Yukawa coupling is tiny, almost nothing on the scale of such couplings. That weakness is part of why the electron is so light and so enduring. This is the original. This is the particle that chemistry depends on, that biology depends on, that the entire visible universe depends on. Every other particle in the Lepton family is defined in relation to it. The muon's Yukawa coupling is larger. The tau's coupling is 20 times larger than the muon's, and about 3,500 times larger than the electrons. Each generation couples more strongly to the Higgs field, which is why each one is heavier. But the standard model does not derive these couplings from anything more fundamental. It measures them. It asks nature what the numbers are, records the answers, and moves forward without asking why. The electron is the anchor. The muon and the tau are copies that grew heavier with each generation, each departing further from the modest, essential stability of the original. And the further they depart, the harder the questions become. The first copy arrived in data nobody was looking for in the 1930s and stopped physics in its tracks. What happened next was one of the most genuinely baffling moments in the history of science. The universe gave physics its first hint that the electron was alone in 1936. The hint came from the sky. Cosmic rays are high-energy particles that rain down on Earth continuously from deep space, colliding with the upper atmosphere at altitudes of many miles and producing cascades of secondary particles that drift down toward the ground. In the 1930s, physicists were using cloud chambers to study these cascades, devices filled with supersaturated vapor in which charged particles leave visible trails as they pass through. Carl Anderson, a physicist at the California Institute of Technology, was examining cosmic ray tracks when he found something that did not belong. A particle with the same electric charge as the electron, curving in a magnetic field the way an electron would, but deflecting far less than an electron of the same energy should. The track was wrong in a precise way. The particle was too heavy to be an electron and too light to be a proton. Anderson was looking at something new. The particle turned out to be about 207 times heavier than the electron. It behaved identically to the electron in every force interaction. It was, by every measurement then available, a copy of the electron with the wrong mass. Nobody had predicted it. Nobody had been looking for it. It arrived in the data like an uninvited guest at a gathering planned around very specific assumptions about who was supposed to show up. The physics community's reaction ranged from bewilderment to frustration. Theorists at the time had been working toward a compact picture of matter. Protons, neutrons, electrons, and a handful of particles to carry forces. The new particle, which became known as the muon, fit nowhere in that picture. It served no obvious structural role. It lived for only about 2/millionths of a second before decaying into an electron and a pair of neutrinos, contributing nothing stable to the world. The Nobel laureate Rabi, speaking for a generation of physicists who had expected the subatomic world to be simpler than it turned out to be, asked the question that has followed particle physics ever since. Who ordered that? It was a genuine cry of confusion dressed as a joke. The muon had been delivered to physics without an explanation attached, and the most uncomfortable thing about it was the precedent it set. If nature could make one redundant copy of the electron, there was no principled reason it had stopped at one. For nearly 4 decades, the muon remained the most puzzling piece of the particle inventory. An unnecessary particle, beautifully measured, completely unexplained. Physicists learned to work with it. The standard model was built around it. The question Rabi had asked was set aside, because physics had more pressing problems to address. Then a physicist in California asked whether 2 unexplained copies of the electron were really the full extent of the story. And the question Rabi had asked grew into something much larger. Most great discoveries in physics arrive because someone builds a better instrument and points it at something. Some arrive because someone decides to look for something that nearly everyone else has agreed to stop thinking about. Martin Pearl arrived at physics through the back door. He was born in Brooklyn in 1927, and his first career had nothing to do with fundamental particles. He studied chemical engineering, earned his degree in 1948, and went to work at a manufacturing company. For several years, he made electrodes, ran quality control, and did the work of an engineer, a professional solving practical problems in industry. But a question would not leave him alone. He had become deeply interested in physics while working, reading whatever he could find, and eventually he made a decision that looked, from the outside, like professional self-destruction. He quit engineering, went back to school, and earned his doctorate in physics from Columbia University in 1955. He was 27 when he started over. His supervisor was Polycarp Kusch, who received the Nobel Prize in Physics that same year. Pearl had chosen physics deliberately, with full knowledge of the cost, arriving late and by design. By the time he joined the Stanford Linear Accelerator Center in 1963, Pearl had developed a reputation for pursuing questions that others found unproductive. He was drawn to particles that conventional wisdom said probably did not exist. He was comfortable with experiments that the field considered a waste of time and resources. He had the temperament of someone who had already changed direction once in life and knew that the conventional path was not the only one worth following. In the early 1970s, the physics community was consolidating around a picture of matter with exactly two lepton generations. The first generation was the electron and its neutrino. The second was the muon and its neutrino. There was no theoretical reason to expect a third. No model predicted it. No experiment demanded it. Pearl looked at this situation and asked a question that more cautious scientists would have kept to themselves. Why not a third? It was a professionally dangerous question. An experiment that searches for a particle that does not exist spends years of career effort and institutional funding finding nothing. You have to be willing to be wrong publicly and at length. Pearl was willing. The machine that made his search possible was just coming online at Stanford. It was a storage ring designed to collide electrons with their antimatter counterparts, positrons, at energies high enough to probe new territory. Pearl understood immediately what such a machine could do, and he began designing the experiment that would define the rest of his career. He was going looking for a ghost. And what he found would force physics to ask Rabi's question all over again, with much greater urgency. The Stanford positron-electron asymmetric ring opened in 1972, and it was elegant in a way that particle physics machines rarely are. Most accelerators of the era smashed protons into targets, producing a messy spray of particles from broken nuclei that experimentalists then had to sort through. The Stanford machine did something cleaner. It took an electron and a positron, the electron's antimatter counterpart, and collided them head-on. When a particle meets its exact antimatter opposite, they annihilate completely. Every scrap of their mass converts to pure energy in an instant. That energy can then reform into new particles, any particles the laws of conservation allow, as long as the total energy is sufficient. What emerges is a controlled burst of creation, starting from nothing but energy and producing whatever nature permits. The physics of this is direct. An electron and a positron meet, vanish, and what emerges is determined entirely by how much energy went in and what conservation laws permit. Vary the energy, and you vary what you can make. Pearl and his team wanted to make a new heavy charged lepton, if one existed. The logic was clean. If there were a third generation of charged leptons following the same pattern as the first two, it would be a particle with a negative charge and a mass somewhere above the muons. Feed enough energy into a collision, and the reaction mechanism would produce it in pairs, one particle and its antiparticle, simultaneously, from the same burst of annihilation energy. The Stanford machine's collision energy could reach up to about 8 billion electron volts. That turned out to be just enough. The detector they used was called the Mark I. It surrounded the collision point with layers of sensing equipment, each designed to catch different types of particles as they flew outward from the center. Charged particles curved in the detector's magnetic field, leaving tracks whose curvature revealed their momentum and charge. The detector could identify electrons and muons specifically, distinguish them from other particles, and measure the energy carried away by the collision products. The trick was that the tau, if it existed, would never survive long enough to reach the detector material. It would appear and collapse within an immeasurably short distance of the collision point, leaving only its decay products to carry information outward. Pearl's search was a search for the pattern of particles a decaying tau would leave behind. The signal he was looking for was specific. If the machine created a tau-anti-tau pair, and one tau decayed into an electron while the other decayed into a muon, the detector would see one electron and one muon on opposite sides of the collision, with significant energy missing because neutrinos produced in those decays would escape without a trace. That combination, an electron on one side and a muon on the other, with missing energy and no accompanying particles, was the fingerprint. The data collection began, and the detector started returning events that nobody had prepared for. The data started arriving in 1974, and something was wrong with it. By wrong, physicists mean something specific. The data showed events that the accepted theory could not account for. Starting that summer, Pearl's group at Stanford began seeing collisions that produced one electron and one muon, flying out of the detector on opposite sides from the same impact point, with significant energy unaccounted for. In the particle physics of the time, this combination was a problem. An electron-muon pair from the same collision had no natural explanation in the framework physicists were working with. Ordinary processes did not produce this signature. A reaction that deposited an electron on one side of the detector and a muon on the other, with large missing energy and no other charged particles, was pointing towards something outside the accepted picture. Pearl's team accumulated these events through 1974 and into 1975, 64 of them, spread across multiple energy settings, all showing the same signature: electron on one side, muon on the other, energy missing. No good explanation for any of it. The interpretation they settled on was straightforward in principle and radical in implication. A new heavy charged lepton was being created in pairs, one particle and its antiparticle from each collision. Each one decayed almost immediately. One decayed into an electron, plus two neutrinos invisible to the detector. The other decayed into a muon, plus two neutrinos, also invisible. The detector saw only the visible products, one electron, one muon, and a gap in the energy accounting corresponding exactly to four neutrinos, quietly carrying momentum into empty space. The mathematics worked. The pattern was consistent. The energies matched. The proposed particle had to have a mass somewhere around 1,800 million electron volts, heavier than a proton, heavier than any known lepton. On the 2nd of December, 1975, Pearl and 10 co-authors submitted a paper. The title was deliberately cautious: Evidence for Anomalous Lepton Production in Electron-Positron Annihilation. They reported 64 unexplained events, proposed a new heavy lepton as the explanation, and sent it to physical review letters. The physics community responded with skepticism, and in some quarters, outright disbelief. The objections were fair. The evidence was entirely indirect. No one had seen a tau. What Pearl had found were tracks left by particles the tau had supposedly decayed into, with the tau itself vanishing before reaching any detector material. Other possible explanations existed, and critics laid them out carefully. The signal could be a background effect. The analysis could have an undiscovered flaw. The new heavy lepton could be a mirage produced by imperfect understanding of known processes. Pearl's paper introduced a particle that existed only as an inference, and the physics community was not ready to accept an inference as a discovery. The tau was about to spend several years in scientific limbo, claimed by one group in California and confirmed by nobody else, while the arguments grew louder on both sides. The reason the tau was so hard to confirm is the same reason it was interesting to find. It died before it could be caught. 290 femtoseconds is the tau's average lifetime. A femtosecond is a millionth of a billionth of a second. Even at the speed of light, 290 femtoseconds is less than a tenth of a millimeter of travel. But the tau, produced in high-energy collisions, moves at close to the speed of light. Relativistic effects stretch the tau's apparent lifetime from the detector's perspective, an effect predicted by Einstein's theory of special relativity, in which a fast-moving clock appears to run slow from the outside. Even so, the tau's path ends in less than 1 millimeter before it disintegrates. No detector technology in 1975 could resolve an object that traveled less than a millimeter from the collision point. The tau existed, collapsed, and left only its decay products to propagate outward. The experiment was like trying to identify someone from the shadows of things they dropped as they vanished. Every piece of evidence for the tau was at least 2 steps removed from the particle itself. The electron in the detector came from a tau, which came from a collision. The muon on the other side came from a different tau, from the same collision. The missing energy belonged to neutrinos the tau had produced, but neutrinos leave no tracks. The entire case rested on inference. These events appear, these other explanations cannot account for them. Therefore, something new must exist. That form of reasoning has a long and successful history in physics. The electron neutrino was proposed the same way, inferred from missing energy in radioactive decay, decades before direct detection was possible. But inference, however careful, is not the same as confirmation. And the physics community, wary of premature announcements, wanted more. Multiple experiments at different laboratories aimed at the same problem through the late 1970s. Some initial analyses raised doubts, finding fewer anomalous events than Pearl's team expected or offering alternative explanations. Others found signals pointing in the same direction but declined to make strong claims before their data was more complete. Each time a new analysis emerged, the community had to weigh its meaning. Science at the frontier is a series of debates, corrections, and accumulating evidence, with the answer becoming clear only once enough independent voices are pointing in the same direction. For nearly 5 years after the 1975 paper, the tau existed in a strange scientific state, proposed but unconfirmed, argued about in seminar rooms and conference proceedings, present in the data of one group and absent from the confirmed results of any other. Pearl continued presenting his evidence. Skeptics continued raising objections. The tau was the most disputed particle in physics. The answer was coming, slowly, from multiple directions at once. And when it arrived, it would carry a weight that went far beyond just confirming a new particle. The confirmation of a new particle in physics is rarely a single moment. It is usually a slow accumulation of evidence from independent sources, each adding weight to a case that eventually becomes too heavy to dispute. For the tau, the accumulation took 5 years. Multiple experiments attempted to replicate or refute Pearl's result through the late 1970s. Some early analyses raised doubts, finding fewer anomalous events than Pearl's team expected or offering alternative interpretations. Others began seeing signals consistent with a new heavy lepton, but declined to make strong claims before their datasets grew large enough. The critical challenge was that every experiment faced the same fundamental problem. The tau left no direct signature. Every argument for its existence was statistical. The rate at which certain event types appeared compared to the rate expected from known processes. Statistical arguments are defensible but slow to convince. They require more events, and then more still, before a signal rises clearly above the background. Pearl presented his evidence at conferences. and in papers through 1976 and 1977, watching the community react with a mixture of fascination and resistance. Some physicists took the results seriously and began building theoretical frameworks around a possible third generation. Others published analyses arguing that the anomalous events could be explained without invoking a new particle. The years passed in a state of productive tension. Nobody had enough evidence to decisively close the question either way. And the tau existed in the physics literature as a disputed claim rather than a confirmed fact. What began to shift the consensus was the gradual convergence of independent measurements. Different experiments using different machines and different analysis techniques kept arriving at a consistent answer. Something with a mass close to 1,777 million electron volts was appearing in their data. The consistency across independent setups was the feature that carried real weight. A single experiment can have a hidden systematic error. 5 experiments at different institutions, with different instruments, pointing to the same mass value, are much harder to dismiss. As the late 1970s progressed, the combined weight of data from multiple experiments began to solidify. The new particle's mass was measured with increasing precision at around 1,777 million electron volts, placing it in genuinely new territory. No known particle had that mass. No known process could easily produce the specific event signatures appearing consistently across different experimental setups at different institutions. By the end of 1979, the physics community had largely accepted the reality of the tau. The evidence, gathered from several different experiments and several different approaches, had crossed the threshold from intriguing anomaly to confirmed particle. The tau became the third charged lepton. The particle was named tau from the Greek letter that begins the Greek word for the third. The choice was deliberate. This was a pattern. The electron, the muon, the tau. 3 members of the same family, arranged by mass, each one heavier and shorter lived than the last. Confirming the tau confirmed that the pattern was real, not an artifact, but confirming the tau did nothing to explain the pattern. In some ways, the confirmation sharpened the question, because now the repetition was undeniable. Nature had made 3 copies of the electron. The experiments agreed on the measurement. The theory had no answer for the reasoning. What came next was the long wait for the recognition that a discovery of this scale eventually brings, and the Nobel Committee, for reasons of its own, was going to make the physics world wait for an unusually long time. 20 years is a long time to wait for recognition of a discovery that reshaped the architecture of particle physics. Martin Pearl waited longer than that. The Nobel Prize in Physics for 1995 was awarded jointly to 2 physicists whose discoveries, made decades apart, had each completed a fundamental piece of the matter inventory. Frederick Reines received his half for the direct detection of the neutrino, a particle that had been predicted in the 1930s and finally caught in 1956. Pearl received his half for the tau lepton. 20 years had passed since the 1975 paper. The field had built entire theoretical frameworks around the particle in that time. Generations of graduate students had learned the tau as settled science before its discoverer held the prize. The Royal Swedish Academy of Sciences, in its citation for Pearl, described him as having found the first member of a 3rd generation of fundamental particles. The phrase carries a sound of triumph. In context, it was also a statement of something deeply unresolved. A 3rd generation implies a pattern. A pattern, in physics, is always evidence of a deeper structure that has not yet been found. Pearl understood this. His Nobel lecture, delivered in Stockholm in December 1995, did something unusual for an address of that kind. Rather than dwelling on what his discovery had established, he spent significant time on what it had failed to explain. He asked directly why 3 generations of matter exist. He called it one of the central open questions in particle physics. He described the search for an answer as a project the field had barely begun. He was right. The question he raised in Stockholm, framed in the careful language of a physicist addressing the world's most prominent scientific audience, was the same question that Rabi had half-jokingly asked about the muon decades before. Who ordered this? Now there were 3 of them. 3 charged leptons, 3 pairs of quarks, 3 families of matter, stacked on top of each other in the Standard Model's equations with no known reason for any of it. Pearl continued working on the tau through the 1980s, 90s, and into the 2000s, contributing to measurements of its properties and advocating for experiments that would push the precision further. He died in September 2014. Having lived to see the Higgs boson discovered, the Standard Model essentially completed, and the tau established as textbook physics measured to extraordinary depth. He did not receive an answer to the question he asked in Stockholm. Neither has anyone else. The tau entered the textbooks carrying 2 kinds of weight. The first was its measured mass, more than a proton, more than a neutron, larger than any charged lepton had any obvious right to be. The second was the open question that its existence forced into the center of physics, the question that the most successful scientific theory ever built cannot answer. That question is what the rest of this story is about. And the place to start is with what the tau actually weighs, and why that number alone is enough to make physicists deeply uncomfortable. Consider what it means for a lepton to weigh more than the nucleus of a hydrogen atom. The tau's mass sits at around 1,703, 77 million electron volts. A proton weighs roughly 938 million electron volts. A neutron is slightly heavier. The tau exceeds both of them combined. It is the heaviest charged lepton in the known universe, and its mass alone places it in territory no lepton has any obvious right to occupy. This matters for more than taxonomy. The electron and muon both sit comfortably below the proton, in the realm of particles too light to decay into the building blocks of nuclei. The tau breaks through that ceiling. Because of its mass, it can do things the other charged leptons cannot, including entering the domain of particles made from quarks. The consequences of that crossing run through every measurement of the tau ever performed. The mass itself comes entirely from one source: the tau's coupling to the Higgs field. After the Higgs field settled into its present state in the early universe, it gave mass to every fermion in proportion to how strongly that fermion interacts with it. Physicists call this the Yukawa coupling, named after the Japanese physicist who formalized the mechanism. The tau's Yukawa coupling is roughly 20 times larger than the muons and about 3,500 times larger than the electrons. That difference is what separates a particle lighter than a grain of dust from one heavier than a proton. But here is what the Standard Model will not say: why the tau's Yukawa coupling has the value it does. The theory takes that coupling as a measured input, a number learned from experiment and inserted into the equations. There is no derivation. No calculation produces the tau's Yukawa coupling from any more fundamental quantity. Ask the equations where it comes from, and the equations return your question with no answer attached. The ratio of tau mass to electron mass is 3,477 to 1. That ratio sits in the Standard Model like a precisely transcribed fact with the source removed. Everyone can read the number. No one knows where it comes from. Physicists have measured the tau's mass with extraordinary care. Multiple independent techniques at multiple laboratories have converged on a value known to within a fraction of 0.1%. The precision of the measurement is impressive. What precision reveals, though, is that knowledge and understanding are different things. Knowing a number to many decimal places says nothing about why that number has the value it does. Astronomers mapped the planet's positions to exquisite accuracy for 2,000 years before anyone understood the gravitational force driving them. The tau's mass is better known than it has ever been, and the reason it occupies its particular location on the mass spectrum remains entirely opaque. There is one consequence of this mass that makes the tau scientifically unique in a way that goes well beyond the generation puzzle. Because the tau is heavier than many particles made of quarks, It has decay channels that are simply unavailable to the lighter leptons. The electron cannot access them. The muon cannot either. Only the tau crosses into quark territory, and it does so in less than a millimeter. That crossing happens so quickly and over so short a distance that describing it requires thinking about time in a register that has almost no everyday equivalent. The tau's lifetime sits in a category of brevity that sits below anything most physics metaphors can easily reach, and grasping it changes how you understand every measurement ever made of the particle. Light travels at about 186,000 miles per second. In the time it takes to blink, light crosses roughly 10,000 miles. In the time a hummingbird's wing completes one beat, light travels nearly 200 miles. These comparisons are useful for developing intuition about the speed of light, but they place you in territory where human experience still serves as a reference. The tau's lifetime sits far below that territory. 290 femtoseconds is 290 millionths of a billionth of bar. A second. In that window, traveling at the speed of light, you would cross less than a tenth of a millimeter, the distance between two adjacent hairs on a human arm. The tau exists, at maximum, for the time it takes light to traverse that gap, and then it is gone. Set this beside the muon, the second-generation charged lepton that the tau is copying. The muon lives for about 2 millionths of a second. That duration has a human feel to it. A fast camera flash fires in roughly that range. Relative to the tau, the muon is essentially eternal. The muon lives approximately 1 million times longer than the tau. That ratio is larger than the ratio between one human lifetime and the age of our planet. The two particles are both short-lived by everyday standards, but they occupy entirely different categories of brevity. The reason for the gap is the tau's mass. A heavier particle has more possible final states available to it when it decays. Each additional final state is an additional exit from existence. The tau, with its enormous mass, can decay into combinations of particles that the muon simply cannot reach, because those combinations require more mass than the muon carries. More exits mean faster disappearance. What prevents the tau from being completely undetectable is a consequence of special relativity. A particle moving at close to the speed of light experiences time differently from an observer at rest. From the detector's perspective, the tau's internal clock runs slow, an effect called time dilation. This relativistic stretching extends the tau's apparent flight distance from a few hundredths of a millimeter to roughly 1 millimeter in a modern high-energy experiment. 1 millimeter sounds modest. Modern pixel detectors, the innermost tracking layers surrounding the collision point in particle physics instruments, can determine positions with a precision measured in tens of micrometers. A tau produced in a collision and decaying 1 millimeter away from the collision point leaves a subtle but measurable signature. Its decay products appear to come from a point slightly displaced from the primary collision. That offset is the tau's fingerprint in a detector, the only trace it leaves before it vanishes. The tau never forms a bound state with another particle. It never participates in any chemistry, even briefly. It appears, travels a distance shorter than a pinhole, hands its energy and quantum numbers off to lighter particles, and disappears. Every measurement of the tau is therefore a measurement of what it left behind. Reading those remnants requires understanding what the tau can decay into, and the inventory of its possible exits is richer than anything the muon or electron comes close to matching. When the tau disintegrates, it does so through the weak nuclear force, the same mechanism governing the muon's decay and the beta decay of radioactive nuclei. A virtual W boson mediates the process, converting the tau's identity into a set of lighter particles. The basic mechanism is well understood. What makes the tau unusual is the number of different things it can become. About 17% of the time, the tau decays into an electron antineutrino, and a tau neutrino. This is the direct parallel of ordinary muon decay, with the tau playing the role of the heavier particle handing its charge and mass off to a lighter lepton. About 17% of the time, the same process produces a muon instead of an electron. Together, these two modes account for roughly 35% of all tau decays. In these cases, the tau behaves like a heavy muon and no surprises emerge. The other 65% of the time, the tau does something that no other charged lepton can do. It decays into hadrons. Hadrons are particles built from quarks. Protons and neutrons are the most familiar, but there are hundreds of others, most of them extremely short-lived. Pions, kaons, rho mesons, a long catalogue of bound quark states with different combinations of flavor and spin. Pions are the lightest, a quark and an antiquark paired into a particle with a mass far below the tau's. A kaon contains a strange quark. These are nuclear world particles, assembled from the same quarks that build the proton. The tau is massive enough to produce them. When the virtual W boson in a tau decay reforms as a quark-antiquark pair, the tau produces a spray of these particles alongside a tau neutrino. The most common single hadronic mode, occurring about 1 in 4 decays, produces a charged pion, a neutral pion, and a tau neutrino. Another common mode produces 3 pions. The full catalogue of hadronic tau decays runs to dozens of distinct measured channels. Experimentalists who work with tau data classify decays by a practical criterion: how many electrically charged tracks appear in the detector. Single-track decays, called one-prong events, occur about 85% of the time. 3-track decays account for most of the remainder. 5-track decays exist but are rare. The pattern of always producing an odd number of charged tracks follows from Lepton number conservation, a fundamental rule requiring that certain quantum numbers remain constant across any decay. An even number of charged tracks would violate that rule, so nature simply does not produce them in tau decays. This diversity of decay modes is a direct consequence of the tau's mass sitting above the hadron production threshold. The electron and muon cannot reach it. The muon is too light by a large margin to produce even the lightest pion alongside a neutrino and still conserve energy. Only the tau crosses that line, and it does so with enough mass remaining to produce a wide variety of hadronic final states. That crossing opens a window onto physics that no other lepton can access. And the view through that window turns out to be scientifically valuable in ways that go well beyond the tau's role in the generation puzzle. Ordinarily, studying the strong nuclear force requires smashing protons or nuclei together and sorting through the debris. Proton-proton collisions are scientifically productive but messy. They produce enormous jets of particles from broken nuclei, layers of overlapping processes, and a tangled signal that analysts must spend years learning to separate from background. The interesting physics sits inside a great deal of noise. Tau hadronic decays offer something different. When the tau produces pions and kaons alongside a tau neutrino, the process begins from a state of near-perfect cleanliness. There are no proton remnants, no nuclear fragments, no ambiguity about what collided with what. A tau and nothing else, decaying through the weak force into a precisely defined initial state. The quark pair that forms the hadrons emerges from a virtual W boson with well-characterized quantum numbers. The environment is controlled in a way that proton collisions can never match. This makes the tau's hadronic decays a precision instrument for studying quantum chromodynamics, the theory of the strong force. Certain quantities in this theory are particularly difficult to calculate from first principles and even harder to measure in other experimental contexts. Specifically, properties of the strong force at energies below the tau's mass, where the interaction becomes too strong for the standard mathematical approximation methods to work cleanly, are areas where experimental input is essential. The tau provides a clean window onto exactly those properties. spanning a range of hadronic energies from threshold up to the tau's mass, all accessible from a single experimental source. One specific application is measuring how strongly quarks attract each other at these energy scales. This quantity, the strong coupling constant evaluated at low energies, is central to several precision tests of the Standard Model. Tau hadronic decays provide one of the most reliable measurements of it available because the initial state is so well understood. The most common hadronic decay mode, producing 2 pions and a tau neutrino, appears often enough that experimentalists use it as a benchmark, a known signal whose rate anchors other measurements throughout tau analyses. Physicists describe the tau as sitting at the boundary between the leptonic and hadronic worlds. Below its mass, that boundary is effectively closed. Electrons and muons interact with quarks only through the weak force at very low rates. Above its mass, other heavy particles also cross between the two worlds, but they do so through entirely different mechanisms. The tau's crossing happens through the weak force, at an energy scale where the hadronic physics is rich enough to be interesting and clean enough to be useful. This dual membership is a consequence of the tau's specific mass sitting where it sits, above the hadron production threshold, but below the region where heavy quark physics dominates. That position traces directly back to the Yukawa coupling, to the Higgs mechanism, to the unexplained number that sets the tau's mass. The tau's unique role as a hadronic probe exists because its mass has the specific value it does. That value has no derivation, and the role itself would vanish if the mass were even slightly different. There is a practical consequence running through every experiment involving taus. Since the particle itself leaves no trace, identifying tau decay products requires instruments precise enough to reconstruct the event from what the tau left behind, and building those instruments has pushed detector physics to its limits for decades. Finding a particle that never reaches your instruments requires building instruments precise enough to read what the particle left behind. The tau's most distinctive experimental signature is called a displaced vertex. In any particle collision, most decay products trace their paths back to the same point, the collision itself called the primary vertex. A tau produced in that collision travels a fraction of a millimeter before disintegrating. Its own decay products originate from a slightly different point, offset from the primary vertex by that small distance. The offset is tiny, far below anything visible to the human eye, but it is systematically different from zero. Modern pixel detectors, the innermost tracking layers wrapped around the collision point in particle physics instruments, can measure positions with a precision of tens of micrometers. Tens of micrometers is a fraction of the diameter of a single human cell. At that resolution, the displaced vertex becomes detectable, a secondary origin point for a cluster of particle tracks appearing slightly separated from the primary collision. Identifying this offset is the first step. Interpreting it correctly is the second. Several different processes produce displaced vertices, and many of them involve particles other than the tau. Physicists have spent years developing pattern recognition algorithms trained on enormous simulated datasets to distinguish the specific signatures of tau decays from everything else that can look similar. When the tau decays, hadronically, it leaves a narrow, isolated cluster of tracks carrying most of the energy in one direction, with less mass than a jet produced by a quark or gluon fragmenting alone. Physicists call this a tau jet. It is compact, pointed, and accompanied by measurable missing energy from the invisible tau neutrino, escaping the detector entirely. When the tau decays leptonically, the signature changes. A tau decaying into an electron leaves a single high-energy electron track with large missing energy from 2 escaping neutrinos. A tau decaying into a muon produces the equivalent with a muon. In both cases, the total visible energy accounts for less than the collision energy should allow. because the neutrinos carry away the remainder undetected. Reconstructing the full tau from these fragments requires combining multiple measurements, accounting for missing energy statistically, and applying constraints from the known conservation laws. The exercise demands deep familiarity with the detector's behavior, with the expected signal and background rates, and with the systematic effects that can mimic the signal. Every generation of detector technology pushes tau identification further. Finer pixel sensors resolve smaller displacements. Faster electronics reduce confusion between overlapping events. Better reconstruction algorithms separate tau decay products from contaminating processes more cleanly. The tau has driven detector physics forward for decades, because identifying it requires solving problems at the edge of what precision instrumentation can achieve. This relationship has an important consequence. Many of the most interesting measurements in tau physics, including tests of a fundamental rule about how all charged leptons should behave, are currently limited by the precision of the instruments rather than by the amount of data available. Push the detectors further, and the science follows. And the rule those instruments are pushing toward is one of the standard model's deepest predictions, emerging from the mathematics of the theory itself. Physics has many symmetries, patterns of behavior that remain constant when you exchange one thing for another. The deepest symmetries fall out of a theory's mathematical structure on their own, unforced from outside. Lepton universality is one of these. It emerges from the equations describing the electroweak force, and it makes a very specific claim. The three charged leptons must couple to the fundamental forces with identical strength. The mechanism behind this is gauge invariance, the organizing principle underlying the entire electroweak theory. When physicists write down the equations for how charged leptons interact with the W and Z bosons, the coupling constant, the number controlling the strength of that interaction, appears as a single parameter shared by all three generations. The mathematics leaves no room for the electron to couple with a different strength than the muon, or for the muon to differ from the tau. One number, 3 leptons. Equal treatment. This means that once you account for the kinematic effects of different masses, the rates of specific processes involving the 3 charged leptons must match exactly. If a W boson decays into a tau, it does so with the same probability as decaying into an electron. If a tau decays into a muon and neutrinos, the rate divided by the rate of decaying into an electron and neutrinos should equal a precisely calculable number. Any departure from those predictions signals something outside the standard model at work. The tau is the sharpest tool for testing this rule. The reason is mass. Picture trying to detect a tiny tilt in a lever. A longer lever moves its far end more for the same tilt, making the effect easier to see. The tau's large mass acts as a long lever that amplifies small deviations in coupling strength into larger, measurable differences in decay rates. A new particle or force that modifies the tau's coupling to the weak force by a tiny fraction would produce a deviation in tau decay rates large enough to detect, while the same modification to the electron or muon might remain buried in measurement noise. This amplification makes the tau uniquely sensitive to new physics that distinguishes between generations. If some hypothetical new force couples preferentially to the tau rather than to the lighter leptons, the tau's large mass magnifies that preference into a detectable signal. Models with extended Higgs sectors, new gauge bosons, and certain classes of leptoquarks all predict this kind of generation-selective coupling. The tau is where the signal would appear most clearly. The prediction is mathematically clean. The measurement is extraordinarily demanding. Testing lepton universality at the level where new physics might be hiding requires accumulating hundreds of millions of tau decays in controlled conditions, measuring their rates with sub-millimeter precision, and isolating every systematic effect that could masquerade as a violation. Current experiments are doing exactly this, and what they have found so far is simultaneously precise and incomplete. consistent with the standard model at the best achievable sensitivity, while leaving room for the new physics that some other measurements are already beginning to suggest. The test has not yet found a crack, but the instruments are still sharpening, and the crack, if it exists, may be just below the current resolution. Measuring the strength of a fundamental rule requires measuring it at the level where it might fail, which means measuring it better than it has ever been measured before. The central test of lepton universality using the tau compares two specific decay rates. How often does the tau decay into a muon antineutrino, and a tau neutrino? How often does it decay into an electron antineutrino, and a tau neutrino? The ratio of these two rates, after accounting for the muon's own small mass, should match a precise prediction if the rule holds. The predicted value is close to 1, with a small calculable correction. Current measurements from the best available experiments find this ratio consistent with the standard model's prediction to within roughly 2 parts in 1,000. That agreement is genuinely impressive. Confirming any prediction at the 2 parts in 1,000 level requires identifying and eliminating systematic errors at that same scale, and particle physics has spent decades developing the tools to do it. 2 parts in 1,000 carries real significance, though. Many theories extending the standard model predict deviations at roughly that level or just below it. Supersymmetric models, theories with extended Higgs sectors, models with new gauge bosons carrying enhanced tau couplings. These tend to produce effects in Lepton universality tests at the fraction of a percent scale. New physics that couples to the Higgs preferentially and involves heavy new particles naturally produces its largest effects in the heaviest charged lepton. The tau is the first place such effects would appear, and they would appear at roughly the level current experiments are reaching. Accumulating the data needed for these measurements requires a specific kind of machine. Only electron-positron colliders running at energies just above the tau pair production threshold can provide the clean, high statistics datasets the measurements demand. At such machines, roughly 8% of all collisions produce a tau-anti-tau pair, with very little hadronic background to contaminate the sample. The Bell 2 experiment at the KEK laboratory in Japan is currently the leading facility for this work, having collected hundreds of millions of tau pairs and continuing to accumulate more. Each improvement in statistical precision pushes the test deeper into the territory where new physics predictions cluster. The most recent single experiment measurement of the coupling ratio finds consistency with the standard model at that 2 parts in 1,000 level. The collaboration aims eventually to push the precision by a factor of several by collecting a dataset 50 times larger than the current one. Both possible outcomes carry scientific value. Finding no deviation at that deeper precision squeezes the allowed space for the theories predicting tau-specific new physics, forcing them to relocate their predictions to still smaller values. Finding a deviation would be among the most significant results in particle physics in a generation. Before reaching those precision measurements, there is an earlier result pointing to the same territory from an entirely different direction. It is a measurement made not by studying how the tau decays, but by studying how a different particle counts. The counting instrument was the Z boson. The answer it produced was a single number, and that number told physics something fundamental about the structure of matter that no other measurement had previously established. By the early 1990s, a machine at the European Organization for Nuclear Research had accumulated enough collisions to answer a question nobody had framed quite so directly before. The Large Electron-Positron Collider had been running since 1989, producing Z bosons in enormous quantities by colliding electrons with positrons at the Z's mass. The Z boson, one of the carriers of the weak nuclear force, decays into pairs of particles almost immediately after being produced, and the rate at which it does so encodes precise information about the Z's properties. Among the particles the Z decays into are neutrino-antineutrino pairs. Each generation of matter with a light neutrino contributes one such pair to the Z's total decay width, More generations with light neutrinos mean more decay channels. More decay channels mean a faster total decay rate, which means the Z's decay width is broader. Measuring the Z's total decay width with high precision is therefore equivalent to counting how many light neutrino species exist in nature. 4 independent experiments at the Large Electron-Positron Collider, each built by a different international collaboration with a different detector design, measured the Z boson's properties during the 1990s. They mapped the production rate at energies above and below the Z mass, fitting the measured curve with extraordinary care to extract the total decay width. Their combined answer was 2.984 light neutrino species, with an uncertainty of about 8 thousandths. The departure from exactly 3 is explained by small known systematic effects in the analysis. What matters is what the number rules out. A 4th generation of particles with a light neutrino would have contributed an additional decay channel, broadening the Z's decay width by roughly 3%. The measured width was narrower. The measurement excluded a 4th light neutrino at a confidence level that experimental physics considers conclusive. The Higgs boson discovery in 2012 added a complementary constraint from a different direction. A 4th generation of quarks would participate in the quantum loop processes controlling how the Higgs boson is produced. Specifically, a 4th generation top-like quark would dramatically enhance the rate at which 2 gluons fuse to produce a Higgs boson. When the Large Hadron Collider measured Higgs production rates, they matched the standard model prediction for 3 quark generations. 4 was incompatible. Nature chose 3 generations precisely. The Z boson measurement puts a ceiling on the count. No direct detection of any 4th generation particle establishes the floor. 3 is the answer from both sides. But knowing the answer is 3 is different from understanding why it is 3. The counting is complete. The explanation is absent. And elsewhere in the theory, a connection exists between that specific count and something with far higher stakes than an aesthetic question about the number of particle families. In the year 1973, 2 physicists working in Japan published a paper that most of the world ignored. Makoto Kobayashi and Toshihide Masukawa were investigating a puzzle that had been sitting in the data for nearly a decade. Certain decays of particles containing strange quarks violated the combined symmetry between matter and antimatter. This violation, called charge parity symmetry breaking, had been measured and confirmed. Where it came from inside the theory was unclear. Charge parity symmetry is the principle that if you replace every particle with its antiparticle and reverse every direction in space, the laws of physics should remain the same. The universe obeys this symmetry almost everywhere. In certain weak force interactions, it breaks slightly. That slight breaking is cosmologically critical. Without it, the early universe would have produced equal quantities of matter and antimatter, which would have annihilated each other completely, leaving nothing but radiation. The imbalance that allowed matter to survive is the reason stars, planets, and living things exist. Kobayashi and Masukawa showed that charge parity symmetry can break within the standard model if and only if the mixing between quark generations is described by a matrix with specific mathematical properties. That matrix must contain a complex phase, a number that cannot be rotated to a real value by any allowed transformation. With a complex phase in the mixing matrix, the theory can violate charge parity symmetry. Without it, the violation disappears entirely. Here is the crucial point. A complex phase can exist in the quark mixing matrix only if there are at least 3 generations of quarks. With 2 generations, the matrix has too few entries to accommodate a complex phase. The mathematics is definitive. 2 generations cannot produce charge parity violation through this mechanism. 3 generations can. The logic runs forward with unavoidable force. Our universe has more matter than antimatter. Therefore, our universe experienced charge parity violation. Therefore, our universe has at least 3 quark generations. The Tau's generation, with its bottom and top quarks, is the minimum required. The calculation also predicted, in 1973, the existence of 2 undiscovered quarks. The bottom quark was found in 1977. The top quark required another 18 years and a machine powerful enough to produce it, arriving in 1995. Both appeared exactly where the theory required them. Kobayashi and Masukawa received the Nobel Prize in Physics in 2008. What this means for the Tau follows directly. The Tau and its neutrino are the leptonic component of the 3rd generation, inseparable from the 3rd generation of quarks. The argument from charge parity violation says that the 3rd generation is the minimum requirement for matter to survive the Big Bang. The Tau's generation might be there because without it, no matter survives, no stars form, no planets form, and no one asks why the Tau exists. That is the strongest case physics currently has for why the Tau is there. It is also incomplete. It explains why a 3rd generation is necessary. It says nothing about why the Tau's mass is what it is, why its Yukawa coupling has the specific value it does, or why the 3rd generation is as extreme a copy of the 2nd as it turns out to be. The argument sets a flaw. Everything above the flaw remains unexplained. Following that argument further requires meeting the Tau's family member that remained unconfirmed for longer than any other particle in the standard models. History. From the moment the Tau was confirmed in 1979, a companion particle was required. Every charged lepton in the standard model structure has a neutral partner carrying the same lepton number and feeling only the weak force. The electron has the electron neutrino. The muon has the muon neutrino. The Tau, by the same pattern, must have a Tau neutrino. The entire theoretical framework demanded it, without question. What the framework demanded and what experiments could deliver were very different things. Every Tau decay produces a Tau neutrino among the final particles. In the leptonic decays, the Tau neutrino carries away part of the missing energy alongside a second neutrino from the lighter lepton. In the hadronic decays, the Tau neutrino escapes alone, taking an invisible share of the event's momentum. The missing energy in Tau decay events required invisible particles with exactly the properties the Tau neutrino was expected to have. The evidence for its existence was continuous and compelling. But evidence of this kind, derived from the absence of energy rather than from a direct signal, is inferential. Pauli had predicted the electron neutrino the same way, reasoning from missing energy in radioactive decay, and that particle's direct detection had required more than 2 decades. The Tau neutrino faced an even steeper challenge. Its production required extremely high energy beams, its interaction with matter was extraordinarily rare, and identifying its specific signature required detecting the millimeter-scale flight path of the Tau lepton it would create upon interacting. Indirect confirmation arrived from multiple directions through the 1980s and 90s. The measurement of the Z boson's decay width at the Large Electron-Positron Collider counted 3 light neutrino species, which had to include the Tau neutrino. The Tau's decay rates required a neutrino with specific properties to balance the energy and momentum accounting. Every calculation involving the 3rd generation assumed the Tau neutrino as a participant, and every prediction that followed from those calculations agreed with experiment. The Tau neutrino was as thoroughly embedded in the theory as any particle in the standard model. For 25 years after the Tau's discovery, no experiment had caught a Tau neutrino producing a visible Tau lepton inside a detector. 25 years is an unusually long gap between prediction and direct confirmation in modern particle physics. Most predicted particles are found within a few years of the machines reaching the energy required to produce them. The Tau neutrino's gap reflected the extraordinary difficulty of the measurement. The team that finally accomplished it built an experiment around one central insight. to directly detect the tau neutrino. You need a source of tau neutrinos in sufficient numbers, a material sensitive enough to record the millimeter-scale decay of the tau it creates, and enough patience to spend years finding a handful of events among millions of interactions. They had all three. Deep inside the experimental halls of the Fermi National Accelerator Laboratory in Batavia, Illinois, a collaboration of physicists spent several years hunting for a particle that had been assumed to exist for a quarter century, but never directly observed. The experiment's name was DONUT, an acronym for Direct Observation of the New Tau. The logic was straightforward. Fermilab's Tevatron accelerator fired a beam of protons at 800 billion electron volts into a tungsten target. The resulting spray of particles included mesons containing charm quarks, called D-subs mesons, which decayed rapidly to produce tau neutrinos. Those tau neutrinos then passed through meters of shielding designed to absorb everything else: electrons, muons, hadrons. What emerged from the far side was a beam concentrated in tau neutrinos, mixed with electron and muon neutrinos. The detector was a stack of iron plates interleaved with nuclear emulsion, a specialized photographic material capable of recording charged particle tracks with a spatial precision measured in micrometers. When a charged particle passes through emulsion and the plates are later processed and examined under a microscope, the track appears as a line of silver grains. The technique had been refined by physicists at Nagoya University in Japan over several decades and had been used to identify particles in cosmic ray events long before modern electronic detectors existed. A tau neutrino interaction inside the emulsion produces a tau lepton. That tau lepton, given its mass and the available energy, travels roughly 1 millimeter before decaying. In emulsion, that millimeter-long flight path followed by the abrupt change in direction as the decay products diverge from the original track forms a distinctive geometry. Physicists describe it as a kink, a checkmark shape embedded in the photographic material. Finding one requires searching through thousands of emulsion plates, examining candidate tracks under a microscope, and measuring the precise geometry of each kink to confirm it matches the expected signature. The collaboration collected data in 1997. Then came the analysis, which took 3 years. Researchers developed algorithms to identify candidate events in the plates, then examined each candidate manually under microscopes. The search was methodical and slow. Tracing the geometry of a kink a millimeter long in a plate exposed to millions of neutrino interactions requires the same combination of precision and patience that archaeologists bring to excavating a buried city with small brushes. They found 4 events, 4 interactions in which a tau neutrino entered the emulsion, struck a nucleus, produced a tau lepton that traveled a fraction of a millimeter, and decayed, leaving its characteristic checkmark shape in the photographic record. 4 events out of millions of interactions, each one a direct observation of a particle whose existence had been assumed for 25 years. On a day in July of the year 2000, the collaboration announced the result. The tau neutrino had been directly observed. The Standard Model's third lepton generation was complete. A charged particle and its neutral partner, both confirmed from direct experimental evidence. The Standard Model's roster was 1 step closer to finished, and the questions surrounding the third generation, about why it exists and whether it is fully obeying the rules, were about to become the most urgent questions in experimental particle physics. Confirmation from the donut experiment said only that the tau neutrino exists and can interact with matter. It said nothing about whether the tau neutrino behaves the way the theory predicts it should behave in the larger framework governing all 3 generations. There was a second, deeper question waiting behind the first. Neutrinos are strange particles by any measure. Unlike most particles, they travel through matter almost without interaction. A neutrino could pass through a wall of lead stretching from here to the nearest star and have only a small chance of stopping. They have almost no mass, but they do have mass, a fact that the original Standard Model did not predict and that physicists discovered in the late 1990s from studying neutrinos produced in the upper atmosphere. And because they have mass, they can do something structurally remarkable. They can change identity while in flight. The process is called neutrino oscillation. A neutrino, produced as a muon neutrino, the kind that accompanies the muon in second-generation decays, will not remain a muon neutrino indefinitely. As it travels, the quantum mechanical components of its state evolve at different rates, and the three types, electron, muon, and tau, mix together and remix continuously. After traveling far enough, a beam that began as purely muon neutrinos will contain a fraction of tau neutrinos. The conversion rate depends on mixing angles, the distance traveled, and the neutrino energies. For this mixing to work fully, at least three flavors must participate. Two-flavor oscillation is a simplified version of the physics. The complete picture requires all three types. And crucially, the full three-flavor framework contains a phase parameter capable of producing the asymmetry between matter and antimatter that the tau's generation requires in the quark sector. Three-flavor neutrino mixing is mathematically parallel to the quark mixing structure that Kobayashi and Maskawa showed must exist for charge parity violation to occur. The tau neutrino is the third ingredient that makes the mixing complete. By the early 2000s, evidence had accumulated that muon neutrinos were disappearing over long distances at rates consistent with oscillation into tau neutrinos. The Super Kamiokande detector in Japan had observed atmospheric muon neutrinos vanishing as they traversed the Earth, and the deficit matched what oscillation into tau neutrinos would predict. But a deficit is an absence. Physics prefers arrivals. The Opara experiment was designed to produce one. Physicists built a massive detector deep inside Gran Sasso Mountain in central Italy, housing thousands of tons of nuclear emulsion plates interleaved with lead bricks inside a structure the size of an office building. They aimed a beam of muon neutrinos at it from the European Organization for Nuclear Research, 700 kilometers away through solid rock. Every tau neutrino that arrived in that beam would have started its journey as a muon neutrino and converted during the passage. The detector ran for years, collecting a beam that operated between 2008 and 2012. Each tau neutrino interaction looked exactly like what the Donu-T collaboration had found. A short track with a kink, the millimeter-scale fingerprint of a tau lepton created and immediately decayed. Finding these events required the same microscopic analysis that had defined the Donu-T search, scaled up considerably. By 2015, the collaboration had confirmed 5 tau neutrino appearance events at the 5 sigma threshold, the gold standard for a discovery in experimental physics. 5 events. Muon neutrinos were arriving as tau neutrinos, precisely as the three-flavor framework required. The confirmation stitched the tau neutrino into the fabric of neutrino physics permanently. The three-flavor structure held, and somewhere inside that structure, a door remained open for the kind of charge parity violation that could explain why the universe has matter in it at all. What makes the tau capable of participating in that structure at the level it does connects back to a question about how it got its enormous mass, and the answer runs through a field that permeates every corner of space. Every particle that has mass acquired it the same way. This is one of the core conclusions of 20th century physics, arrived at after decades of theoretical work and confirmed experimentally with one of the most celebrated discoveries in the history of science. In the moments after the universe began, the conditions were too extreme for matter as we know it to exist. The temperature was high enough to destroy any structure before it could form, and the fundamental particles moved through the environment without the property we call mass. Then, as the universe cooled through a specific threshold, a field that permeates all of space settled into a stable configuration, a state it maintains today throughout the observable universe. That field interacts with certain particles, and the interaction itself is what we experience as mass. The field is called the Higgs field, named for the Scottish physicist Peter Higgs, who helped develop the theoretical framework for it in 1964. The particle associated with the field is the Higgs boson. Its discovery at the Large Hadron Collider in 2012 was the culmination of a search lasting nearly half a century. Each fermion couples to the Higgs field with a strength described by a number physicists call the Yukawa coupling. A particle with a large Yukawa coupling acquires more mass. A particle with a small one acquires less. The electron's Yukawa coupling is tiny. It acquires a mass smaller than any other charged particle. The tau's Yukawa coupling is roughly 3,500 times larger, and the tau acquires a mass larger than the proton. Here is what the theory cannot tell you: why the tau's Yukawa coupling has the value it does. The standard model treats the coupling as an input, a parameter measured by experiment and inserted into the equations. There is no calculation, no derivation, no deeper principle from which the tau's coupling emerges. Ask the theory why the tau couples to the Higgs so much more strongly than the electron, and the theory says, that is what we measure. The answer and the question become the same thing restated. This became more than abstract in 2014. The experiments at the Large Hadron Collider announced the first direct observation of a Higgs boson decaying into a tau and an anti-tau. That particular decay mode had been expected. The Higgs couples to massive particles, and the tau is the heaviest charged lepton, so the coupling should be large enough to produce a measurable signal. The signal appeared in the data at the level the theory predicted. The observation mattered for two reasons. First, it confirmed that the Higgs couples directly to third-generation leptons, establishing experimentally that the tau's mass comes from exactly the mechanism the theory proposes. Second, it opened the door to precision measurements of that coupling, testing whether the Higgs couples to the tau at exactly the standard model strength or at a slightly different value that would indicate something beyond the known theory. Current measurements find the Higgs-tau coupling consistent with the standard model prediction within the available precision. But the precision has not yet reached the depth where many theories of new physics predict their effects to appear. Better measurements of the Higgs-tau coupling are among the primary goals of the next generation of accelerator experiments. What the Higgs measurement tells you is that the connection between the tau and the Higgs field is real and directly confirmed. What it does not tell you is where the strength of that connection comes from. The tau is heavy because it couples strongly to the Higgs. Why it couples so strongly remains a question the theory cannot answer from within. That unexplained coupling, combined with the tau's large mass, makes the tau uniquely sensitive to new physics lurking at higher energies. And beginning around 2012, a set of measurements involving a completely different particle began producing results that suggested something in the tau sector might actually differ from what the theory predicts. Something had been quietly accumulating in PREDICT. The data at an accelerator laboratory in Menlo Park, California, and the physicists watching it were beginning to wonder whether the standard model had developed a crack. The particles at the center of this story are B mesons. A B meson is a composite particle containing a bottom quark. The quark that sits in the third generation alongside the tau in the lepton sector and was predicted in 1973 before anyone had ever seen it. B mesons are produced copiously in electron-positron colliders tuned to the right energy, and they decay through the weak force into combinations of lighter particles. Among the particles they can produce are leptons, and the standard model predicts precisely what fraction of B meson decays should produce each type. Lepton universality, the rule established earlier in this story, applies here as well. Because the W boson mediating B meson decay couples with equal strength to all three charged leptons, a B meson decaying to a lepton should show no preference among the three generations, apart from calculable kinematic effects from their different masses. The ratio of decays producing a tau lepton compared to decays producing a muon or electron should equal a precisely calculable number. The Barbar experiment at Stanford measured this ratio in 2012, using data collected from several 100 million collisions recorded over several years. The observable they constructed compares how often a particular type of B meson decay produces a tau relative to how often it produces a lighter lepton. The measurement was higher than the standard model predicted. The excess was at roughly 3.5 standard deviations above the theoretical expectation, a level physicists describe as a strong hint rather than a discovery. But its direction was clear. B mesons were decaying to tau leptons more often than they should. The immediate response from the broader physics community involved the usual combination of interest and caution. An excess at 3 or 4 standard deviations appears regularly in particle physics data and routinely vanishes when more data arrives or when systematic uncertainties are re-examined. The history of the field is filled with hints that promised discoveries and delivered nothing. Barbar's result was taken seriously, but held at arm's length. Then the Bell experiment in Japan measured the same observable using a different detector and a different dataset at the KEK laboratory. Bell found an excess too. The LHCb experiment at the Large Hadron Collider, studying B meson decays in a different production environment with different systematic uncertainties, measured a related observable. The excess appeared again. The pattern was unusual. Multiple independent experiments, built on different technologies and located on different continents, were finding the same directional preference. B mesons appeared to prefer decaying to tau leptons over the lighter ones more than the standard model said they should. The collective tension between the measurements and the prediction, maintained by a global group tracking heavy flavor averages, grew to roughly 3.8 standard deviations by 2025. 3.8 standard deviations is a strong hint. It carries a probability of arising from random fluctuations small enough to justify sustained investigation. And the fact that this particular excess involved the tau, specifically the tau, was beginning to feel less like a coincidence and more like a pattern. Something, if the excess was real, was coupling differently to the tau. Whatever that something was, the standard model did not contain it, and the story took a turn that made the tau excess harder to dismiss. For more than a decade, as the B meson anomaly in the tau sector accumulated evidence, a second B meson anomaly developed alongside it, pointing in a different direction. This second anomaly involved the relationship between muons and electrons. B mesons decaying into a kaon and a lepton-antilepton pair should, by Lepton universality, produce muon pairs and electron pairs at nearly equal rates. A certain measurement comparing these two rates had been showing a deficit on the muon side for several years. The muons were appearing less often than expected relative to the electrons. By the early 2020s, the combined tau anomaly and the muon-electron anomaly were both being cited as possible evidence of physics beyond the standard model in the B meson sector. Some theorists built models explaining both with a single new particle. The scientific discussion treated the two anomalies as related phenomena pointing toward a common underlying cause. Then, in 2022, LHCb reanalyzed the muon-electron measurement with improved methodology. The collaboration had developed a new analysis approach that used the electron and muon decays of the B meson itself as a reference, cancelling certain systematic uncertainties that had complicated previous analyses. When they applied this approach to their full dataset, the anomaly disappeared. The ratio of muon to electron decays came back consistent with the standard model's prediction. The earlier excess had been a systematic artifact, a bias from how the events were selected and reconstructed. The revision was significant. One of the two pillars supporting the case for B anomaly, physics, had been removed entirely. The tau excess remained. This asymmetric outcome is instructive in a way that goes beyond just tallying which anomalies survived. The muon electron anomaly disappeared when systematic uncertainties were better controlled. The tau anomaly has now been measured by 4 separate experiments using different methods and data, and the excess has persisted. Each new measurement has slightly different central values and uncertainties, and some individual measurements sit closer to the standard model than others. But the combined average has stayed above the prediction for over a decade. Persistent excess in the tau channel after the muon channel normalized is exactly what certain classes of new physics would produce. Theoretical models exist that couple new particles specifically to the third generation, enhancing tau couplings while leaving muon and electron couplings nearly unchanged. In these models, the muon-electron ratio would be standard model consistent, and the tau excess in B meson decays would be real. The data, as it currently stands, is broadly consistent with this pattern. Broadly consistent is different from confirmed. An anomaly at 3.8 standard deviations has a probability of arising from random fluctuation that demands continued investigation without yet crossing the threshold for claiming a discovery. The community is watching. What makes the situation scientifically compelling is that it is specific. The anomaly appears in a particular observable, involving the tau specifically, measured by multiple independent collaborations, and has persisted for over a decade. If it is a fluctuation, it is an extraordinarily stubborn one. If it is real, it points directly at the tau as the particle where the standard model's grip is loosening. And if something beyond the standard model is preferentially coupling to the tau, the question becomes, what is it? 3 classes of hypothetical particles have emerged as the leading candidates for explaining why B mesons might be breaking the standard model's rules in the tau sector. Each represents a different way of extending the theory to accommodate a coupling that prefers the tau over the lighter leptons. The first candidate is the leptoquark. As the name suggests, a leptoquark carries properties of both leptons and quarks simultaneously, and it can convert between the two categories, bridging what the standard model treats as separate sectors of matter. In the standard model, quarks and leptons do not directly transform into each other. A leptoquark would allow them to, and depending on which specific type of leptoquark exists, it would do so with preferences for certain generations over others. A leptoquark coupling preferentially to bottom quarks and tau leptons would enhance the B meson tau decay rate in precisely the observed direction. Several specific leptoquark models have been constructed that can reproduce the measured excess while remaining consistent with other data. The challenge is that leptoquarks also leave signatures in other processes. Any new particle mediating a quark to lepton conversion will affect multiple observables simultaneously. Building a model that fixes the B meson tau excess without creating conflicts in other measurements requires careful engineering, and current attempts produce fits that work but feel constructed rather than natural. The second candidate is a charged Higgs boson. In the simplest version of the Higgs mechanism, there is a single Higgs field and a single physical Higgs particle. In many extensions of the standard model, there are 2 Higgs fields, producing a richer set of physical particles, including a charged counterpart to the electrically neutral Higgs boson already discovered. A charged Higgs, if it exists, would mediate B meson decays in a way that couples more strongly to heavier leptons because of how the Higgs mechanism works. The coupling to a lepton is proportional to the lepton's mass. That proportionality means the charged Higgs would favor the tau over the muon and electron, amplifying the tau rate in B decays. This feature is appealing because it connects the tau anomaly directly to the tau's large Yukawa coupling, tying the anomaly to the same unexplained feature of the tau that defines its place in the generation puzzle. A charged Higgs explanation would mean the tau is special because of its mass, and its mass is special because of its Higgs coupling, and that coupling is the thing nobody understands. The third candidate involves new heavy-gauge bosons. The weak force is carried by the W and Z bosons, and these are the only particles the standard model allows to mediate the relevant decays. Theories with extended gauge symmetries predict heavier versions of these bosons that could couple to quarks and leptons with strengths differing from generation to generation. A heavier W-like boson that couples more strongly to tau leptons than to muons or electrons would enhance B meson decays to tau pairs in exactly the way the anomaly requires. Every one of these explanations shares a structural feature, a new particle or force that treats the tau differently from the lighter leptons. Every one of them also faces the same problem. Fitting the B meson excess creates predictions for other processes that have been measured and found consistent with the standard model. Making the models work requires precise parameter tuning to avoid contradictions elsewhere. Theorists describe the situation accurately. The B meson tau excess can be explained, but no clean explanation has emerged. Something coupling specifically to the tau is the common thread. Whether that something is a leptoquark, a charged Higgs, or a new gauge boson remains unresolved. Finding out requires more data. And right now, the most powerful source of that data sits in a facility on the main island of Japan. Japan hosts the world's most capable tau physics experiment, and it is running right now. The Bell 2 detector operates at the Super KEKB accelerator at the KEK laboratory in Tsukuba, roughly an hour northeast of Tokyo. Super KEKB is an asymmetric electron-positron collider designed to produce enormous quantities of B mesons and tau pairs. The asymmetry in beam energies means the collision products travel forward in the detector, allowing precise measurement of displaced vertices. The facility set a world record for instantaneous luminosity in 2022, meaning more collisions per second than any other electron-positron machine in history. At the energy at which Bell 2 operates, roughly 8 of every 100 collisions produce a tau and an anti-tau together. The machine runs continuously, accumulating tau pairs at a rate that, over months and years, yields statistics unachievable by any previous experiment. By 2025, the collaboration had collected data from hundreds of millions of tau pairs. The detector's innermost tracking layer is a silicon pixel detector with position resolution measured in tens of micrometers. Tens of micrometers is a fraction of the diameter of a single human cell. At that resolution, the displaced vertex that identifies a tau decay becomes detectable. Its decay products appear slightly offset from the collision point, a signature that could easily be missed by any less precise instrument. This pixel detector was upgraded during a major maintenance period in the early 2020s, and its performance has enabled measurements that previous detectors could only approach. Bell 2 has used this capability to produce several significant tau results. The most precise single experiment test of lepton universality using tau decays, published in 2024, found the coupling ratio between tau decays to muons and tau decays to electrons consistent with the standard model at roughly 2 parts in 1,000. That precision is a current limit, expected to improve by a factor of several as the dataset grows. The experiment has also produced new world-best limits on certain rare tau processes, including the most stringent limit ever placed on a tau decaying into 3 muons. That search, completed with a fraction of the ultimate planned dataset, already sets a constraint that many theories of new physics are straining against. Measurements of the tau's mass at Bell 2 use a method based on reconstructing specific hadronic tau decay modes, exploiting the clean electron-positron environment and the detector's momentum resolution. The results provide the most precise single experiment determination of the tau mass in history, contributing to the global average used by the particle physics community. The collaboration's ultimate goal is a dataset 50 times larger than what currently exists. At that scale, sensitivity to lepton universality violations, rare decay modes, and mass measurements will reach levels where any new physics coupling specifically to the tau must either reveal itself or be definitively excluded across a broad range of theoretical possibilities. Bell 2 is joined by LHCb at CERN, which continues measuring meson decays, involving tau leptons with complementary methods and a different production source. Future facilities now being designed, including a possible circular electron-positron collider capable of producing enormous numbers of Z bosons, would dwarf even Bell 2's ultimate dataset and push tau physics into territory currently beyond reach. The most scientifically explosive of all possible future results would come from finding the tau doing something the standard model says it should never do under any circumstances. Some processes in physics are forbidden the way 2 + 2 = 5 is forbidden in arithmetic. The rules simply do not allow them. In the standard model, each type of lepton carries a separate conservation number. Electron lepton number, muon lepton number, and tau lepton number are each independently preserved in all interactions. A tau lepton carries tau lepton number of +1. When it decays, the total tau lepton number of the products must also be +1, which means a tau neutrino must appear in the final state. A tau cannot transform into 3 muons, or a muon and a photon, or a muon and a pion, because none of these final states contain a tau neutrino. They would violate tau lepton number conservation. In the standard model, these processes technically do occur because neutrino oscillation introduces a tiny mixing between lepton generations at the quantum level, but the resulting rate is so unimaginably small, below 1 in 10 million billion for most channels, that no conceivable experiment could detect it. For all practical purposes, the standard model says these decays are impossible. This absolute prohibition is precisely why finding one would be the clearest signal of new physics in a generation. Virtually every theory extending the standard model predicts lepton flavor violation in tau decays at rates far above the standard model's effectively zero baseline. Supersymmetric models, which introduce partner particles for every known particle, generate loop diagrams where tau leptons can convert to muons through the exchange of virtual superpartners. Leptoquark models allow quark-lepton conversion that produces lepton flavor violation as a side effect. Extended Higgs theories often predict charged Higgs particles with off-diagonal couplings between lepton generations. All of these mechanisms produce tau decays into final states without a tau neutrino, at rates between 1 in 100 million and 1 in a billion. Those rates are exactly where current experiments are searching. A tau decaying into 3 muons is among the most theoretically motivated and experimentally clean channels. 3 muons from a single tau decay produce a very specific signature, 3 charged tracks, all muons, with a combined mass equal to the tau mass and a combined momentum pointing back toward the collision. Bell 2's most recent limit on this process is below 2 in 100 million. Reaching that sensitivity required hundreds of millions of tau pairs, precise track reconstruction, and careful control of background processes that could mimic the signal. Other channels are being pursued simultaneously. A tau decaying into a muon and a photon. A tau decaying into a muon and a neutral pion. A tau decaying into combinations of electrons, muons, and heavier mesons. Each channel tests a different piece of theoretical space. The full catalogue of search decay modes runs to several dozen distinct processes. The current generation of searches has found no signal. Each null result tightens the constraint on the theories predicting lepton flavor violation, shrinking the allowed parameter space. Some supersymmetric models have already been pushed to corners of their parameter space that physicists describe as unnatural. The next phase of Bell 2 data collection is expected to push the sensitivity by roughly an order of magnitude in the most important channels, reaching levels where models predicting lepton flavor violation in the tau sector must either produce a signal or be substantially abandoned. If a signal appears in the next few years of data, it will change everything. If nothing appears, That too will be a profound statement about the tau and about the structure of whatever lies beyond the standard model. But before returning to the laboratory, there is a place the tau played a role that no experiment can revisit. The first microsecond of the universe's existence. Rewind the universe approximately 13.8 billion years, past galaxies, past the first stars, past the moment when hydrogen atoms cooled into existence, past the epoch when protons and neutrons locked together into nuclei, past the moment when quarks were first able to form hadrons at all, to a time when the temperature of the universe was so extreme that the familiar particles of ordinary matter could not exist as stable structures. At 1 microsecond after the Big Bang, the universe was a thermal bath of extraordinary density and temperature. The average energy of each particle in the bath exceeded the rest mass energy of the tau lepton. Conditions like this allow particles and antiparticles to be created from pure thermal energy in a continuous process. When the temperature provides enough energy, a particle and its antiparticle are born from the radiation field, exist briefly, find each other, and annihilate back into radiation in an endless cycle of creation and destruction. Tau and anti-tau pairs were being created and annihilated at prodigious rates in the first microsecond. The tau was a full constituent of the cosmic plasma then, present in enormous numbers throughout the universe, continuously being made and destroyed as the universe expanded and cooled. This had consequences. The tau and the anti-tau, appearing in the thermal bath and annihilating back into it, contributed to the total energy density of the early universe. Energy density drives the expansion rate. A universe with more energy in its thermal bath expands faster. The tau's contribution to the energy density during its active epoch shaped the rate at which the universe cooled, which in turn affected the timing of other processes downstream. The tau itself did not survive this period. As the universe expanded, the average temperature fell. When the typical particle energy dropped below the tau's rest mass, pair production of tau pairs became energetically impossible. The existing taus decayed within their 290 femtosecond lifetime. The tau population dropped to 0 and stayed there. The universe had passed through the tau's active epoch and moved on. The tau neutrino outlasted its partner. Neutrinos decouple from the thermal bath earlier than charged particles because their interactions with ordinary matter are so weak. The tau neutrino, produced in tau decays and in other weak interactions during the early universe, became part of the cosmic neutrino background, a thermal relic persisting to the present day. Every cubic centimeter of the universe contains on average about 56 tau neutrinos from the Big Bang, passing through everything around you right now without stopping. Measurements of the cosmic microwave background and of primordial nucleosynthesis are sensitive to how many neutrino species contributed to the early universe's expansion. The measured value of this quantity, called the effective number of neutrino species, is consistent with 3, meaning 3 light neutrino types contributed to the early universe's energy budget. The tau neutrino's share is included in that count. The universe that the tau helped shape in its first microsecond went on to build everything visible in it entirely from first-generation particles, up quarks, down quarks, and electrons, organized into protons, neutrons, atoms, molecules, stars, galaxies, and eventually planets where creatures evolved to build accelerators to rediscover the tau and wonder why it was there. The tau's cosmic role was brief. The question it leaves behind has lasted 50 years and counting. The strongest argument physics currently has for why 3 generations exist rather than 2 or 4 comes from a connection established in 1973, before the tau was confirmed, before the bottom quark was found, before anyone knew for certain that a third generation existed at all. The argument runs from the matter-antimatter problem backward to the generation count. Our universe contains vastly more matter than antimatter. Galaxies, stars, planets, and living things are all made of matter. The antimatter that existed after the Big Bang appears to have been destroyed in collisions with matter, and the slight excess of matter survived to become everything visible. For this to happen, there must have been a slight asymmetry in how matter and antimatter were treated by the early universe's physical laws. A universe where matter and antimatter are perfectly symmetric produces nothing after the Big Bang. Every particle finds its antiparticle, and both disappear in radiation. Kobayashi and Maskawa showed in 1973 that the mathematical structure describing how quarks mix between generations can accommodate this asymmetry. But only under a specific condition. There must be at least 3 generations of quarks. 2 generations produce a mixing structure that is real rather than complex. A real mixing matrix cannot generate the asymmetry between matter and antimatter. A complex mixing matrix can. 3 generations are the minimum required to introduce a complex phase into the quark mixing matrix, and 3 generations are therefore the minimum required for the Standard Model to contain the charge parity violation that a matter-dominated universe requires. The implication for the tau follows directly. The tau and its neutrino are the leptonic component of the 3rd generation, inseparable from the 3rd generation of quarks. The 3rd generation includes the bottom and top quarks, the quark mixing with the complex phase, and the mechanism through which the Standard Model can produce more matter than antimatter. The tau's generation might be there because without it, no matter survives, no stars form, no planets form, and no one asks why the tau exists. This is a genuinely satisfying connection. It elevates the tau from a redundant copy to a cosmological necessity. But the argument has a precise limit. It establishes that 3 generations are necessary. It says nothing about why the tau's mass sits at 1,777 million electron volts rather than at 500 million or 3,000. It says nothing about why the tau's Yukawa coupling is 20 times the muons. It says nothing about why the 3rd generation is as extreme a copy of the 2nd as it turns out to be. The Kobayashi-Maskawa argument sets a flaw. Everything above the flaw remains unexplained. Some physicists extend the reasoning into anthropic territory. Among all possible universes with all possible parameters, only those producing enough matter to form stars and planets can produce observers to notice. We are, by definition, in a universe where the conditions for our existence were met. If exactly 3 generations of quarks are required for matter to survive the Big Bang, then we will always find ourselves in a universe with at least 3 generations because the others produced no one to ask the question. This argument is logically valid. Many physicists find it deeply unsatisfying. The honest position is that the 3rd generation's existence may be cosmologically necessary, while its specific properties remain without explanation. The tau sits at the intersection of what we can explain and what we cannot. Its generation's existence can be argued from the matter-antimatter asymmetry. Its individual properties, its mass, its coupling, the precise way it differs from the muon and electron, require a deeper theory than physics currently has. Whether that theory can be found is the question that the last decades of tau research have been building toward, one attempt at a time. Beneath the Standard Model's precision lies a layer of structure the theory cannot access, and physicists have been trying to reach it through multiple routes for decades with persistent, partial success. Prion models represent one attempt. The idea is that quarks and leptons are structured objects assembled from still smaller constituents, the way protons are assembled from quarks. In these models, an electron, a muon, and a tau are the same prionic structure in different energy configurations, the way an atom can exist in a ground state or excited states. The mass hierarchy between generations would then reflect the energy cost of the different configurations, providing a structural reason for why the tau is heavier than the muon and the muon heavier than the electron. The appeal is real. The explanation would replace the standard model's unexplained Yukawa coupling hierarchy with a mechanical picture of internal structure, grounding the generation puzzle in geometry rather than in mysterious free parameters. The problem is that high-energy collisions have found no evidence of quark or lepton substructure. If quarks and leptons were composite, the composites' internal dynamics would produce deviations from point particle behavior at energies above the compositeness scale. Experiments at the Large Hadron Collider have searched for these deviations at energies far beyond what any reasonable preon model expected to survive undetected, and found nothing. Preon models cannot be definitively ruled out, but the space available for them has shrunk to dimensions requiring the compositeness scale to be implausibly high, removing the explanatory power that motivated the models in the first place. String theory approaches the generation puzzle from a different direction entirely. In string theory, the fundamental objects are one-dimensional strings vibrating in higher dimensional spaces. The number of generations of matter particles depends on the topology of the extra dimensions curled up beyond the 4 dimensions of ordinary space and time. Specifically, the generation count equals a topological quantity called the Euler characteristic of the compactified extra-dimensional space. For the correct extra-dimensional geometry, the theory naturally produces exactly 3 generations. This is genuinely compelling. 3 generations emerging from geometric topology rather than from a free parameter would be a deep structural explanation. The difficulty is that nobody has derived the complete standard model from string theory from first principles. String theory can accommodate 3 generations for the right compactification, but it can also accommodate other numbers for other compactifications. Without a principle that selects the right geometry, the generation count prediction is conditional rather than necessary. Grand unified theories offer a related approach. Certain mathematical symmetry groups, when broken down to the standard model's symmetry group, naturally produce 3 copies of the matter content as part of the group's representation structure. The 3 generations emerge from the algebra of the larger symmetry in a way that feels natural rather than imposed. Again, the results are suggestive rather than definitive. The generation structure fits the mathematics of large symmetry groups, but no grand unified theory has been confirmed experimentally, and deriving the specific mass hierarchy from the group structure remains an unsolved problem. The most recent serious attempt to derive the mass hierarchy came from theoretical work published in the years around 2020, which proposed treating third-generation masses as fundamental and having lighter generations acquire mass through quantum loop corrections. The tau's mass would set the scale. The muon would acquire mass from virtual tau interactions. The electron would acquire mass from virtual muon interactions. The chain would explain why each generation is lighter than the previous one and would tie the mass ratios to calculable quantum corrections. The results get the rough order of magnitude right, but fail to reproduce the precise, measured values. The idea is beautiful. The numbers do not quite work. As physicists who have examined this approach observe, it gets you most of the way there. Most of the way has never been the answer. Every framework that has been tried captures something real about the generation structure while failing to fully explain it. The pattern of partial success is itself a clue, suggesting the answer exists and that existing theories are approaching it from different directions without yet converging. Something is close. Nothing is there yet. 50 years have passed since a team at an accelerator in California noticed 64 events that no known particle could explain, and the mystery those events opened has not closed. The tau lepton is now one of the most precisely characterized particles in all of physics. Its mass is known to within a fraction of 1,000%. Its lifetime is measured to better than 1 part in 500. Its decay rates have been mapped across dozens of distinct channels, many of them measured to accuracies below 1 in 100 million. The coupling that gives it mass has been directly confirmed through Higgs boson decays. Its role in the three-flavor neutrino mixing framework has been established from observations on opposite sides of the Earth. Its family is complete. The tau neutrino was directly observed in 2000, and its transformation from muon neutrinos was confirmed 15 years later. Precision and understanding are different things, and the tau makes this distinction sharper than almost anything else in science. Every measurement described in this story tells us what the tau does and how it behaves. None of it tells us why it exists, why it weighs what it weighs, or why nature built 3 generations of matter rather than 1. The Standard Model is a theory of extraordinary accuracy and peculiar honesty. It tells you what particles exist, what forces act between them, and what quantities those particles carry. It accepts its own ignorance about where those quantities come from. The tau's Yukawa coupling is a number in the equations of the Standard Model, the same way the radius of a circle is a number you provide to find its area. The math works perfectly once you supply the input, and the theory has nothing to say about where the input came from. The generation puzzle is the clearest example of this limitation. Ask the Standard Model why there are 3 generations, and it returns the question unanswered. Ask why the tau is 3,477 times heavier than the electron, and you receive the same silence. The model's extraordinary precision at describing the tau is entirely consistent with knowing nothing about its origin. What physics does know is that the question carries cosmological weight. The tau's generation may be the reason the universe contains matter. The complex phase in the quark mixing matrix requires 3 generations, and without that phase, the symmetry between matter and antimatter remains unbroken, and the universe that forms after the Big Bang is empty. The tau might be the particle whose generation's existence is the condition for the existence of everything else. That argument is the closest physics has come to an answer. It is still incomplete. The meson anomaly, if it survives growing scrutiny, will be pointing at new physics coupling specifically to the tau. The forbidden decay searches at Bell 2 are probing the territory where several leading theories predict visible signals. The precision Lepton universality tests are reaching the depth where generation-selective new forces would have to show themselves. These are active searches, running right now, producing new data every month, converging on the territory where the tau's deeper story either reveals itself or becomes harder to locate. Martin Pearl stood in Stockholm in 1995 and asked why 3 generations exist. He had found the tau 20 years earlier, spent 2 decades watching the mystery deepen, and received the prize while the central question remained open. He worked on it until the end of his life and did not find the answer. Rabi asked who ordered the muon in 1936. The answer, it turned out, was that the universe ordered 2 more after that, and it refused to explain itself. The tau sits inside the most successful scientific theory ever constructed like a perfectly measured question. Every property confirmed to extraordinary depth, every attempt to explain those properties falling short by the same margin. A particle that builds nothing in the everyday universe, that exists for less than the time it takes light to cross a single human cell, that arrived without invitation and without explanation. Precisely measured, persistently unexplained, patiently waiting for a theory deep enough to finally say why.